You're about to enter one of the most complex objects ever built by humans. It fits in the palm of your hand. It runs at over 1 billion operations per second, and most people have absolutely no idea how it works. Today, we go inside a GPU. All right, before we shrink down and fly inside, we need to understand one fundamental thing. A CPU, the brain of your computer, is like a single genius. One super smart core doing tasks one by one. A GPU? That's an army. Thousands of smaller workers all doing simple math at the exact same time, in parallel. That parallel power is why your games look incredible. It's why AI can process millions of images. It's why we're even able to have this conversation. For example, this is the diagram of RTX 40 series. The diagram shows a GPU PCB from a bird's eye view, the green circuit board you'd see if you took a graphics card apart. Here's the big picture. The GPU die sits at the center of everything. It's the brain. 6 GDDR6X memory chips surround it, 3 above, 3 below, connected by a 384-bit bus, meaning data travels on 384 parallel copper traces simultaneously, which is how VRAM achieves hundreds of GBs of bandwidth. On the right side, the VRM and PWM controller handle power delivery. Your PSU sends a raw 12V through the 16-pin connector, and the VRM chops that down to the precise sub-1V levels the GPU die actually needs. This is critical because even a 0.05V error could crash or damage the chip. The display outputs HDMI plus DisplayPort on the far right are the final stop. Once the GPU finishes rendering a frame into VRAM, it reads it back and sends it down those purple traces to your monitor. The animated traces in the original diagram represent real electrical signals. Dashed patterns moving along the copper traces show the direction and relative speed of data flow at any given moment. Video RAM, or VRAM. Think of this as the GPU's short-term memory. Everything the GPU needs, textures, frame data, model weights, lives here. Modern GPUs have between 8 GB and 80 GB of VRAM. The more you have, the bigger the worlds you can render, the bigger the AI models you can run. Data moves in and out of VRAM at speeds over 1,000 GB per second. That's fast enough to copy an entire HD movie in a fraction of a millisecond. The shader cores. If VRAM is the warehouse, this is the factory floor. A high-end GPU has thousands of these tiny processors. Each one can do floating point math incredibly fast, and they all work together on the same problem simultaneously. Here's the magic. Imagine you need to calculate the color of every pixel on your screen. That's over 8 million pixels in 4K. A CPU would do them one by one. The GPU sends thousands of cores to tackle them all at once. Boom! Instant frame, 60 times a second. So, how does a 3D world actually become pixels on your screen? It starts with geometry. Your game sends thousands of triangles to the GPU. Every object in the scene is made of triangles. The vertex shader takes those triangles and positions them correctly in 3D space. Then the rasterizer converts those 3D triangles into 2D pixels on your screen. Then the fragment shader, also called a pixel shader, decides the exact color, lighting, and texture of every single pixel. All of this happens dozens of times per second, for millions of pixels, simultaneously. Modern GPUs have 2 secret weapons hidden inside them. Tensor cores, designed specifically for AI and machine learning. They can multiply giant matrices of numbers at insane speed, which is exactly what neural networks need to think. And ray tracing cores. These simulate how light actually behaves in the real world. Reflections, shadows, the way light bounces off a wet street at night, all calculated physically accurately in real time. So there you have it. Inside your GPU, a tiny universe of billions of transistors working in perfect harmony thousands of times every second. Whether you're gaming, doing 3D work, or running AI models, this chip is doing something genuinely extraordinary, and now you know exactly how. If you found this interesting, subscribe, because soon we will be working on a robot. See you there!